Welcome back. So we were just going to look at the solution to the sequence problem. So where are we? Okay. So again, when marginal utility is always positive, and if it is go to positive infinity when C goes to 0, this implies CT is always positive. Then this implies this is always positive. Then lambda T is always positive. This implies resources are always used. So then I can write the 2. Then since this will be always positive, there is no capital left for tomorrow by the rational decision maker in this particular problem, right? But I also know something else. If consumption will be positive for all T, then I need all of these to be positive, right? Why? Because F0 is 0. So capital is an essential input. So if all these capital stock levels will be positive, then this equation, this one, this first order condition that I'm just going to show you. So this one, okay, for periods from 0 to T minus 1 will hold with equality as well. So I will have lambda T equals lambda T plus 1 times F prime KT plus. Okay. So then I know the evolution of lambda as well. So if we count the equations, so obviously now this is starting from 0 and going to T, right? This equation. This one is also starting from 0 and going to T minus 1. At the very end, we have FKT equals CT, right? Because there's no capital stock left. And this one also starts from 0 and ends at T minus 1, because at the very end, I will have lambda T minus 1 equals lambda T F prime KT. Okay. So then I have a dynamical system of 3 variables, right? This is a dynamical system. So let me show you the equations. This one, and this one. All right. So what are the conditions? Well, there is an initial condition and there is a terminal condition now. Okay. So what about C0 and lambda 0? Well, they're going to be chosen to satisfy this constraint and this constraint, right? So at the very end, so since this is an optimal growth problem, you know that some sort of a saddle point will be the steady state, right? So the steady state will be a saddle point. So to be on the saddle path at the initial period, the consumer or the decision maker more generally will choose C0 and a particular lambda 0, of course, so that they jump at the initial period so they jump on a point that is on the saddle path. Okay, so you know that part. And now what you can do with this system is this, of course. You can let me just rewrite it. So you have that, you have that, and you have that. Again, initial condition is given, terminal condition is given, right? So you can derive the Euler equation basically, right? Now, be careful what I am doing. So I'm iterating the first equation one period further, right? So then I replace these into the co-state equation. So I have what? I have beta t u prime ct being equal to beta t plus 1 u prime ct plus 1, okay, times f prime kt plus 1, right? So beta t's cancel out, and eventually I have u prime ct divided by u prime ct plus 1 equals beta times f prime kt plus 1. So this is your, of course, Euler equation, right? So it tells you how you can substitute today's and tomorrow's consumption. And of course, once again, you are looking at the marginal productivity of capital and your discount rate. Sorry, discount factor. By the way, I forgot to mention this. So here, you may always assume that. So if rho is the discount rate, beta is the discount factor. All right, so you should be careful with this terminology. All right, you know that rho is positive. In that case, consumer is impatient. And if rho is positive, beta is always less than 1. Okay, beta is always between 0 and 1. Okay, so this ensures that they discount at the same, you know, I mean, so these functions. So if this is t, let's say this is discrete, right? So this is beta t, and then you have e to the minus rho t, right? Here t is continuous. So the pace of decrease will be the same. Okay, that's the notion. Under this constraint, I mean, under this relationship, that must be the case. All right. So if, for instance, you think about this in terms of linear utility and Cobb-Douglas production function, right? That was the case that we solved for. The continuous time problem. Then what do you have? You have 1 over ct plus 1 equals beta times alpha kt plus 1 alpha minus 1. All right, so in other words, you have ct plus 1 divided by ct equals beta alpha kt plus 1 alpha minus 1. All right, so that becomes your Euler equation. Okay, so you can do that, and then you can look at the steady state, because this is just a dynamical system now, right? So a steady state will satisfy, of course, these conditions, right? This one, forget about lambda for a moment. So you have u prime c star divided by u prime c star equals beta f prime k star. So here in this equation, you have beta f prime k star equals 1, right? So this tells you k star. Then if you know k star, the first equation tells you what c star is. Okay, so that's how you solve for the steady state. And then after solving the steady state, of course, you can linearize the model, and you can do all the, you know, stability analysis, all the other stuff that you learn. Let me show you one other trick. Okay, so you have in the first equation, you have this, right? So then this equation actually is not, it's not stationary, right? It depends on time, but you can always define some other value, such as the current value, right? So you put this on the other side, and then you have u prime ct equals mu t, right? So then your system becomes stationary even in mu as well, right? Now the obvious question is this: can we generalize this into t going to positive infinity, right? That's an important thing, because in most problems, in most cases, we are interested in infinite dimensional problems. So the time horizon of the model is infinite. Okay, it turns out that it's very simple, because only this changes. Remember this constraint? Now, what does it tell you again? So it is just complementary slackness, right? For the last period, if it is valuable, so this tells you two things. If it is valuable, then you should eat all of it. If it is not valuable, you can leave some of it, or you can still eat all of it. Okay? So this is just complementary slackness, and only this part will change, because first order conditions other than this one will remain the same, right? So how does this change when t goes to positive infinity? Then obviously we take the limit. Right? I mean, we just take the limit. Okay? And that's it. Then you have still the same first order conditions. All right, so what are they? Well, you have beta t, u prime ct equals lambda t equals lambda t plus 1, f prime kt plus 1. Then you have kt plus 1 plus ct equals f of kt, all right? Then you again have the initial condition, and then you have, of course, the transversality condition, okay? And in most of the time, we replace lambda t there, so you have beta t, u prime ct, kt equals 0. Okay? So that's it. Now, as you see, we can very easily generalize the system, but still, usually we do not use this sequence approach. All right, there's a couple of reasons. I mean, there are a couple of reasons for this. Now, one is that it is computationally extensive. All right, so you are choosing infinite sequences, right? You are choosing this. And that goes on. Then you are choosing K1, K2, KT, and that goes on. You are choosing lambda 0, lambda 1, lambda t, and that goes on. Okay, you are choosing all these. And one other problem is that you cannot, in the problems that where there is an analytical solution, you do not find this policy function. Okay, so we want to be computationally more appealing, a finite dimensional version of it. All right, so that the recursive approach is doing exactly that. And recursive approach, as it turns out, is very, very attractive from a computational perspective, because you know, it allows us to do that in a machine. all right, in a computer. And then there is also the stochastic versions, all right. In the stochastic problems, when there are shocks around, it is also easier to work with the recursive approach, all right. So now I'm going to show you what this recursive approach is. But before that, I have to refresh your minds about the value functions, all right? So forget about the dynamics for a moment and think about a very simple consumption problem, okay? So this is static consumption problem, all right? So there's this utility function, then there's this price vector, okay? And then there's the income, right? So there's non-negativity constraints, okay, as well. And here, of course, the price vector and income are given. Okay, so this is positive prices, this is strictly positive income, right? Now, if this problem has a solution, so if you maximize this by choosing a vector of consumption levels subject to these constraints, if this problem has a solution, you find this solution in this way, right? So for each I, you have a function that expresses your solution in your givens, okay? So that solution is expressed in terms of givens. Then you write the indirect utility function, right? So indirect utility function is written in this way. So it is C1 star, C2 star, dot, 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 Cn star. So it is C1 PW, C2 PW, right? Cn PW, okay? So at the end, it is a function of prices and income, okay? So this is called value function. So this is found when we insert back the optimum policies, right? So don't forget, the solution is not just the numerical value you choose there. The solution is this function. So there is this function here, okay? This is the solution. All right? So if you put back these solutions back in to your original objective function, what you find is called value function. Okay? And of course, our problem, the simple optimal growth problem, or any other discrete time dynamic optimization problem, if it can be solved through the sequence approach, then there must be a value function there, right? You understand that. So there is a value function out there if we are maximizing the intertemporal utility function, this animal, if we are really maximizing this stuff, okay, from t equals 0 to positive infinity, if we really maximizing this by choosing optimal consumption levels, then there must be, of course, some value function. But what does this function a function of? What is that function a function of? Okay, so we want to understand that. And now to understand that, we have to go and try to understand how the sequence approach really solves the problem. Okay, so the problem is again this: maximize from t equals 0 to positive infinity beta t uct, right? So this function is uc0 plus beta uc1, right? Plus beta square uc2, and that goes on. Okay, and we are choosing an entire sequence of consumptions subject to our constraints. Okay, Now, what is the first thing we have to choose? Well, the first thing we have to choose is, of course, given our state, we choose C0, right? And then budget constraint and C0 gives me K1. And then I choose C1, K2, and then I choose C2, K3, and that goes on. Now, if you imagine this carefully, what I am really doing must be involving solving the problem at the very beginning, at t equals 0, right? Because I want to find a plan and I execute this plan. Remember, in that model, for instance, so this is a saddle point problem. So I have to choose C0 in a particular way so that at the very end, I do not go to the point where it violates the transversality condition. I do not go into a point where that violates the feasibility constraint. I go to a point exactly that positive capital stock and positive consumption level. And to do that, I choose that point initially, and that must be planned, okay? Planned from the very beginning. Well, how do I do that? Of course, we are assuming that the agent is capable of doing that, right? But at the very end, this value function, if it really exists, must be only a function of this, because the only given is this, right? So in the static consumption problem, the only givens are these, right? As I just explained. So here, for the consumer, the only given is the initial capital stock. All right? So then the value function must be a function of this. All right? So so that's one idea, that's one starting idea for how we should think about the recursive approach. Okay? Now, here comes the fun part. Let's rewrite this function in the following way. Okay? So if this is really maximizing, then we must have this, right? So U star plus beta U C1 star, right? Plus beta square U C2 star, and that goes on. Now, here is the trick. Let's do this. You see what happened? Well, if I choose, so now we have two parts, right? So the first part maximizes my current utility, okay? And the second part is the maximized value of the problem starting today, okay? At the end of today, I mean, starting at the beginning of period 1, and its discounted value, right? So if I choose C0 optimally, what does it mean? I'm leaving, if I choose C0 optimally, I'm also choosing K1 optimally, right? But this is just VK1 star. Okay? This is just VK1 star. Okay? Right? Because this is the same form. Look at this. I mean, you can change the time index anywhere, right? So suppose that the problem does not start at t equals 0, but it starts at t equal 5. Okay? It has the same form. It can start anytime t hat. All right? So if, of course, I'm assuming that this is the maximized value, right? So here I am assuming that I'm choosing C0 optimally, but if I choose C0 optimally, I have to be choosing K1 optimally as well. Then I have this form. All right. So if I rewrite this, I have VK0 equals U C0 star plus beta V K1 star. Okay. Now that's the first step. The second step involves this. Instead of writing this in the maximized form, I can write this as a maximization problem. Okay, I can write this as a maximization problem. And then, since the problem can start from anywhere, I can write this in this way. Okay, now this animal is called the Bellman equation. Okay, it's called the Bellman equation. And now I expressed my problem, and of course I still have my constraints, right? These constraints are there, don't forget them. Oops. And K0 is given. Now I expressed my problem in a very different way. Okay, but it is still the same problem. Why? Because if I am choosing CT and KT plus 1 optimally to maximize this part, right, then this V function will be, or let's say must be, the same V function, all right? So these functions has to be the same, all right? And I must be, of course, obeying the constraints with the same V function at the end, and I must be choosing CT, of course, optimal, all right? But as you see, it is recursive, right? Because I am not now looking for the entire sequence. So this is now from this point on, it becomes a little bit more technical, but the idea is that this is an equation that solves a function. All right. So if you are looking for an unknown here, that unknown is a function V. Okay. I will explain that. So don't be just upset. So it will all make sense once you see the entire set of lectures in these 3 weeks. But the idea is that now I express the very same problem in basically a 2-period problem. It is now a 2-period problem because I am not dealing with infinite sequences. Okay. Now, assuming that you don't have anything to ask because you remain silent, let me show you this. Now this is the same equation. Okay. And this is CT, this is KT plus 1. Okay. Now suppose that you actually characterize the optimal policy with this function, all right? And then your constraint written as an equation, basically, because we know that utility will be increasing, so all the resources are used in any given period. So you can write KT plus 1 as KKT. So this is basically FKT minus CKT, right? So just for one moment, you suppose that you know that, knowing that you know that, right? So you have something like this. Since this is now maximizing it, I'm gonna write the maximized version, and KT plus 1 must be equal to FKT minus CKT. Okay. Now, if you know C, if you know this function, you can find V. All right. This is, again, let me write with capital letters. This is a functional equation. So this equation solves functions, okay? Not numbers. It's not algebraic right now. It is functional, all right? Now, if you know CKT, you can solve this equation for V. Or if you know V, okay, if you know V, you can solve this part. You can solve this part for CT equals CKT, right? The problem is that we don't know either CKT or VKT. That's the problem. So both are unknowns, okay? So dynamic programming, the official name that Richard Bellman has given, dynamic programming resolves this problem, okay? Dynamic programming techniques allow us to solve this functional equation in a very articulate ways, in very different articulate ways. So very smart, very intuitive, and I will show you how. For now, let me just stop for another break. We have 4 minutes for your questions. Now it's better, obviously better, if you have any confusions, just ask. Just indicate these confusions so I can re-explain again. I can try my best. I can try different strategies because this is essential. So basically, so let me give you a very quick summary. We applied nonlinear programming techniques to a problem of dynamic optimization in discrete time. We found a dynamical system. Then we generalized that to an infinite size problem with an infinite, so a problem of dynamic optimization with an infinite horizon. Then we used the concept of value function, okay? Pretty standard in static optimization theory, right? In the consumer choice, you write the indirect utility function as a function of prices and W. These are the things that are given to the consumer. So here, that given is capital stock at the beginning of period, all right? At the beginning of any period. And for if the problem starts at t equals 0, K0 is the only thing that is given to the consumer, so the value function must be a function of that. But then, since there is additive separability in the utility function, in other words, of course, this is about time consistency, right? So these additive preferences allow this consumer or the decision maker to be time consistent. So at the very end, we're gonna find policy functions. We're gonna find policy functions. As you see, the function does not change, only the argument changes, right? So once we solve this problem through dynamic programming techniques, we find the policy function that does not change in time. So the consumer does not change the plan. Only the capital stock changes. Okay, and changing capital stock allows the consumer to reflect on the consumption choice by changing the output argument, right? the function itself remains the same. So in that case, we call them, of course, time consistent. All right, now you have 2 minutes before the break to ask questions. Of course, you can ask your questions after the break as well, but that's the Bellman equation. So if you have any trouble with that, just raise your hand. Okay, let's take another break. It is around 2:35 here. So let's meet at 2:50, okay? At 2:50, we're gonna continue with the dynamic programming or the recursive approach.
Okay.
All right, bye-bye.